You forget your password. The website sends you a link to set a new one. What it never does is send you the old one. Not the biggest sites, not the smallest. Nobody. That is not politeness, and it is not a policy. They genuinely do not have it. Your password is not in their database. So what is in there instead? I built a small database, leaked it to myself, and then broke into it 3 different ways to find out. Every number in this video was measured on this laptop this morning. Where I am reasoning rather than measuring, the screen says so. Start with what replaced the password. This is how it used to work. A column of usernames, and next to it a column of passwords, sitting there in plain text. One break-in, and every account is gone at once. And because people reuse passwords, so is their email, and their bank, and every other site they used it on. So the fix is to not store it at all. Store something you can check a password against, without that something being the password. Run it through a one-way function. Here is the real output for the word sunshine, and underneath it, the same word with the last letter changed. Not a similar answer, an unrelated one. The same input always gives the same output. One character different gives you something with nothing in common, and there is no way to run it backwards. So logging in becomes simple. Hash whatever you just typed, compare the 2 strings, let them in if they match. The website never needs the actual password. Ever. Which sounds finished. It is not, and I can show you why using nothing but the stolen file. Here are 6 rows of the hash database. Look at Anna, Dev and Gus. I have no idea what their password is, but identical inputs give identical outputs, so I know all 3 picked the same one, and that it is the most popular password in the file, which makes it the one to guess first. And that is the real attack. Nobody reverses a hash. They guess a password, hash the guess, and see if it matches a row. I generated 100,000 likely passwords, hashed the list once into a lookup table, and read every account straight out of it. 10 out of 10, in 9/100ths of a second. Notice what did not happen. Nobody broke the mathematics. The hash did exactly what it promised. It was simply outrun. There is a well-known fix for this, and almost everybody who has heard of it has heard the wrong thing about it. Give every account its own random number, called a salt. Mix it into the password before hashing. Then store it next to the hash, in plain sight. It is not a secret. Here are those same 3 accounts again, still sharing one password. 3 different salts. 3 completely different hashes. The duplicates vanish. And the lookup table I spent all that effort building is now worthless, because every hash in it assumed no salt. So I have to start over, per account. Unsalted, the list was 100,000 hashes in total. Salted, it is 100,000 for Anna, then again for Dev, then again for Gus. 10 accounts, 1,000,000 hashes. Which sounds like a real defense until you time it. 9/100ths of a second became 85/100ths. 10 out of 10 still fell. This is the part almost every explanation gets wrong. A salt does not make one guess any harder. What it does is stop a single pre-computed table covering everybody, and multiply the work by the number of accounts. That is all of it. And under 1 second is not security. Salting is necessary. It is nowhere near sufficient. Something in this has to be slow. Which brings us to the only change that actually worked. The problem was never the salt. It is that the hash is fast. SHI-256 was built to check downloads, where fast is exactly what you want. Here, fast is the bug. So use a different hash, one designed from the start to be slow. The one I measured is called bcrypt, and it has a dial on the side of it called the cost. Turn the dial, and the time per hash climbs. 19 milliseconds, 35, 68, 139, 313, 607. Each step up is meant to double the work, measured rung by rung. They came out between 1.8 and 2.3, close enough that the doubling is real, not close enough to call it exact. And that is the entire design. You pick the largest number your servers can afford on every login. The attacker, who pays it millions of times over, inherits your choice. Same guest list, same 10 accounts, same laptop, with a salted fast hash under a second. With bcrypt it cost 3.5 days. I should be exact about that. I did not sit here for 3 days. It is the measured cost 12 rate multiplied by 1,000,000. Arithmetic, not a timing. Per hash, the gap between the fast hash and the slow one came out at roughly 500,000 to 1. That is one setting in one line of code, chosen on the day the site was built. Push it as far as it goes. Every possible 8-character lowercase password is 208 billion combinations. At my fast hash rate, 1.4 days. At the bcrypt rate, about 2,000 years. So is that the end of it? Not quite, and the reason is a good one. Bcrypt was designed in 1999, and what it spends is processor time. Modern cracking does not run on processors. It runs on graphics cards. Thousands of small cores, all doing the same thing at once. The newer answer, Argon 2 ID, spends something much harder to multiply. I measured it at its own library defaults. 54 milliseconds and 64 megabytes of memory for one single hash. Time is cheap to copy 1,000 times in parallel. 64 megabytes each, 1,000 times over, is 64 gigabytes of graphics memory. That is the point of it. Before the answer, the usual honesty. This time it cuts against me harder than usual in 2 separate ways. 1. My fast hash figure is a Python loop, and most of what it measures is Python. The same chip in bulk, with the language out of the way, did 21 million a second, 12 times faster. So every attack time here is a floor, not an estimate. A machine built for this is far past either number. What transfers is the ratio between the 2 hashes, not the seconds. 2. I ran this whole measurement file twice today. The fast hash reproduced within 4%. Bcrypt at cost 12 came out at 273 milliseconds, then 313. A 14% spread on the same laptop an hour apart. So treat 3 days as an order of magnitude, not a number. And it was never safety anyway. It is time. Enough for a company to notice the breach and tell everyone to change their password. And none of it saves a password that is on the guest list at all. Bcrypt makes the 100,000th guess expensive. It does nothing about the first one. So, back to where we started. Because the row in their database is not your password. It is a random salt, a number saying how slow to be, and a fingerprint that can be checked but never read backwards. Which hands you one useful test. If a website ever emails you your actual password or reads it back over the phone, they stored it. And you now know exactly what that means. The best thing a website can possibly know about your password is almost nothing at all. Thanks for watching.